everyone, welcome to Organolysis. So this is our rearrangement reaction part 2, and in this video we are going to talk about benzylic acid rearrangement, which is very much important for your CSIR-NET, GATE, and as well as your university exam and BSc MSc entrance exams also. Okay, now let's start. The first compound that is being used for this benzylic acid rearrangement is alpha diketone. Okay, and if you use a base like OH minus or the base nucleophile like this OH minus alkoxide or amide ion. Okay, so here I am taking this OH minus as a nucleophile, and it will attack to this carbonyl carbon, and you get this type of product. Now how this type of product that you get, that is this R group will selectively migrate to the center, and that is why you get this kind of intermediate, and after this hydrolysis, that is you get this protonation of this O minus. Okay, and that is how you get this type of product. This is important concept, that is your alpha diketone and your alpha diketone or this 1,2-diketone. Okay, so this is very much important substrate for this benzylic acid rearrangement. Now this is a one kind of 1,2 shift, and I will show you when we discuss about this mechanism of this reaction. Okay, now you have this 1,2-diketone that is cyclic 1,2-diketone, and if you use a nucleophile like OH minus, and you get this type of intermediate, that is a 1,2 shift via a ring contraction method. Okay, so you can see over here, that is you have the 6-membered ring, and after this nucleophilic attack you get the 5-membered ring over here. So this is 1,2 shift via a ring contraction. Okay, and after this hydrolysis you get this C=O minus to C=H. Okay, now let's discuss the mechanism, which is very much important for this reaction. That is this OH minus or the nucleophile selectively attack to this ketone like this. It will attack to this ketone and this O minus over here, and you get this type of tetrahedral intermediate. Okay, so the reaction goes through this tetrahedral intermediate. Okay, and this O minus is now back like this, and this R group will migrate to this carbonyl center, and this bond will open up to this side. Okay, then you get, this is our 1,2 shift, and then you get this type of acid over here, and you have the O minus, and after this proton transfer. Now why this proton transfer takes place? Just because of if this O minus directly takes the proton from here, just because of you get this negative charge over here, and this negative charge is stabilized just because of it has a conjugation like this. Okay, and this is your alpha hydroxy acid salt. Okay, so this is your overall mechanism for this benzylic acid rearrangement. Now see why the name of this reaction is benzylic acid, not or anything else. Okay, now see the first studied compound, that is the first studied 1,2-diketone, is the benzyl. Okay, now what is the structure of benzyl? Now I'm written over here, that is this is the structure of benzyl, that is your benzyl. Okay, now this benzyl, if we selectively treat this OH minus, and after the rearrangement it will attack over here, goes over here, and this migrate to this center, and this like this. Okay, and the product that you get is this is your pH, this is your COOH, and this is your OH. So this is your benzylic acid. Okay, so benzylic acid. This reaction is also named as benzyl to benzylic acid rearrangement. Okay, so selectively that is called benzylic acid rearrangement. Okay, now see the importance, some example of this reaction which is important for your exams. Okay, so that is the example, and I will show you the different kinds of example of this benzylic acid rearrangement, and after that we will also discuss some semi-benzilic acid rearrangement. Okay, so let's first see the examples. Okay, so the first example, here I am taking the two different types of carbonyl over here, just because of you can see over here that here you have this methoxide substituted in this phenyl group, and you have the only phenyl group over here. Now this we all know that this has a plus R effect of this OMe group, and it will also donate to this negative lone pair of oxygen lone pair electron. It can donate to this center, and these bonds go over here, and these bonds go over here, and like this. Okay, now see this electrophilicity of this carbonyl is selectively decreases just because of this ring is present to this adjacent to this carbonyl. and that is why this OH minus is nucleophile is selectively attacked to this carbonyl, not to this carbonyl, not to this carbonyl, just because of this reactivity is loses by introducing this group. Okay, now see what happens next. Like this, it will selectively attack to this carbonyl. You can see that this OH minus is directly attacked to this carbonyl just because of it is more electrophilic compared to this one. So just because of this plus R effect, and it will loses the selectivity electrophilicity of this carbonyl group. Okay, now see, this will happen. This O minus, here is your tetrahedral intermediate, and here you have the phenyl group like this. Okay, now then this O minus is back to say here, and this phenyl group is migrate, which is bond pair electron, and this go over here. Okay, then finally the product that you get. Now I am not writing the overall protolysis or hydrolysis of this reaction. I will show you the only product. Okay, this C double bond O, this is your OH, this is your C double OH. Okay, not this is your OH, this is your C double OH, this is your, I'm not in, only in pH. Okay, so this is how you can get this type of product. Okay, this is your C double OH. Now the one more important example of this benzylic acid rearrangement is this one. Okay, now I think you all know the name of this compound, that is your phenanthrene. Okay, so this is your phenanthrene. Okay, so now the phenanthrene is selectively, and how can you get this type of product from phenanthrene? You can easily use this Cr2O7 in acetic acid. Okay, if you use this in K2Cr2O7 in acetic acid, you get this type of compound, that is 9,10-phenanthroquinone. I'm putting 9,10-phenanthroquinone. Okay, so this is your 9,10-phenanthroquinone, and you can, if you use this type of alcoholic OH over here, we all know what will be the product. There is a 6-membered ring. We already shown over here, that is a 6-membered 1,2-diketone is selectively ring contracted to get this type of 5-membered ring. Okay, so this similar thing also happened over here, and you will also get this type of 5-membered ring. This go over here, and this bond will migrate, and this like this. Okay, I am not writing the overall mechanism. I will show you the overall, the final product. Okay, so this is how you can get this type of product. Okay, this is your OH, this is your C double OH. Okay, so this is your final product. Now let's see the one more example of this reaction is that if you have this type of compound, that is it is called furyl. It is called furyl, and after the using of this NaOH and the H2O plus, you get the furylic acid. Okay, so this is your furylic acid. Now that is how we can get this type of product. Okay, now let's see one more example of this reaction is this. Okay, now the one more important, the similar kind of examples I'm written over here, which is very much important, and this is not just direct benzylic acid rearrangement, but it is a benzylic acid rearrangement in different way. Okay, so see, you have this OH minus over here, and you have this 2 methyl substituted in this 2 phenyl group. Okay, and if you use this OH minus, it will selectively takes a proton from here, just because of it is comparatively more acidic. That is why it is takes a proton from this CH3 unit, and it will generate a selectively CH2 minus, and this CH2 minus directly attack to this carbonyl carbon, and you get this type of 5-membered intermediate, and the final product like this after this hydrolysis. Okay, so let's see the next example, that is if you have a 3-membered ring over like this, and if you use this nucleophilic OMe minus, and this OMe minus takes a proton from here, and you have this O minus, and this O minus is go back over here, and this bond is migrate to this carbonyl carbon, and this O minus back over here, and you get this type of 4-membered ring. And this 4-membered ring is very much important, that is it is aromatic in nature. Okay, now see why it is aromatic. It is aromatic just because of it has a 4n+2 rule. It follows 4n+2 rule, and here is a n equal to 0, that is 2 pi electron. Okay, and it is aromatic compound. Okay, now this is a dipositive center. This is one more important example, and see the last example of this benzylic acid rearrangement is that you have a substrate like this one. There is a 1 chloro, here is a 1 chloro, there is a 2 chloro group over here and here, and this OH minus is attached to this carbonyl carbon, and these bonds go for this O minus, and you get this O minus back over here, and it will migrate to this center, and this Cl will leave from the system. And that is how you can get this type of there is a 2 4-membered ring, and you have in the junction you have this COOH and Cl. Okay, and you have in the reaction medium you have this OH minus, so it will take a proton from here just because of it is acidic, comparatively acidic, and after this hydrolysis you get this type of product. Okay, so this is an important example for the benzylic acid rearrangement. Now let's come to the semi-benzylic acid rearrangement, and it is also important for your exams. Okay, and question also asks from this topic. And see, this is your alpha haloketone. Okay, so the alpha haloketone contains no alpha hydrogen, and when it is treated with this alkoxide, and it will follow the semi-benzylic acid pathway. Now what is semi-benzylic acid rearrangement? That if you have this alpha haloketone and you have this nucleophile, that is alkoxide, this OR minus attack to this carbonyl carbon, and this go back to here, and O minus over here, and this O minus goes to the center, and this R group is selectively migrate to this center, and the Cl will leave from the system just because of Cl is a very much good leaving group, and that is why you can this type of rearrangement takes place, and it is called semi-benzylic acid rearrangement, and that is how you can get this type of product. That is kind of ester. Okay, now see the important example of this reaction is that if you have a compound like this, that is a 4-membered ring, and with a bromine substituted, that is alpha bromo compound of this. Now if you use this OH minus over here, this OH minus attacks to this carbonyl carbon, and this bonds goes to back to the oxygen side. Here that this O minus goes back to the here, and this will migrate to the sand Br, and it will leave from the system, that is Br, leave from the system, and we get this final product. Now there is a one more important pathway of this reaction is that you can see that this is your acidic hydrogen, so it is OH minus takes a proton from this side, and here you have the negative charge, and negative charge attached to this center, and you have the Br is leave from the system. And this kind of intermediate and this type of pathway is not followed just because of you have this intermediate, and this intermediate is very much unstable just because of the very much strained ring. Okay, so this is your very much strained ring. Okay, so that is why this type of pathway is not followed over here, and this kind of pathway is followed generally Favorsky rearrangement. Okay, that is a Favorsky rearrangement, but this type of compound generally not shows the Favorsky rearrangement, and it will follows the semi-benzylic acid pathway. And I also made a and if you don't know what is the Favorsky rearrangement, I also made a video on Favorsky rearrangement. You can go over here and check this video for a Favorsky rearrangement. Okay, now let's see the last and important example of this semi-benzylic acid rearrangement is that if you have a compound like this, and that is a alpha haloketone, and if you use this base, that is OH minus or nucleophile, and this nucleophile attacks to this carbonyl carbon, here you have the O minus and you have the OH, and this O minus backs to here, and this pH will migrate to the center, and this Cl will leave from the system, and you get this type of acid. Okay, so this is how the semi-benzylic acid rearrangement takes place. Okay, and I hope this video is very much helpful for you, and if you find this video useful, share it with your friends, and that's it for this video, and thank you so much for watching.